Hey guys, hopefully you have already watched the Edpuzzle to get us kind of jumped off on this chapter about electrostatics. If you haven't, please stop this and go do that first. It's going to introduce all these ideas, but otherwise, here we go. This is kind of a summary page. I have decided to do this instead of notes with you guys since you're all pretty good students. I think you can kind of use this and maybe we can do some underlining on key ideas instead of doing the notes. But so the big idea of this chapter is that electrostatics involves electric charge, the forces between them, and the behavior in materials. So this is not new information, I hope, right? So we have like charges repel, opposite charges attract. This is kind of a key idea. This is electricity at rest. Okay, so we have charges on different materials that can attract or repel each other, but it's not like we're talking about electrical current. Okay, it's charge at rest. So this is all some atom basics rehash here. So protons are in the nucleus, they're positive, and electrons are flying around outside the nucleus. We know opposites attract. So the positive protons in the nucleus pull the negative electrons toward the nucleus, stop them from flying away, and the electron's momentum and repulsion from other electrons kind of keep them in balance around the atom. Okay, so when we're talking about charge, okay, we say that electrons have a charge of negative E, E being, the actual amount of charge that an electron has, and protons have a charge of positive E. Neutrons, we know, have no charge, neutral, neutrons, and so they don't really have an attraction or repulsion by either of the other particles. Okay, conservation of charge. We have seen this word in science over and over and over again. It always means the same thing, cannot create or destroy. Okay, so conservation of charge. We can move charge, we can transfer charge, but we cannot make it and we cannot destroy it. Okay, ions are a word we use for anything that has charge. Okay, ions have charge. And so if something has more protons than electrons, it'll have a positive charge. If it has more electrons than protons, it will have a negative charge. Okay, so now what do we do with this information? Okay, so we're in physics, so we always have to have a little fun and do some math with it. And so our math is Coulomb's law, and I don't like particularly the way it's written here, so I'm going to rewrite it up here. So the force between two things equals K, which is a constant. Okay, this is K. Okay, if we're dealing with air or vacuum, that's pretty much K. If we had two charged things attracting or repelling each other in a different medium, we'd use a different K, but for the most part, things are either in air or they're out in space. So this is going to work. And then we have on the top of a fraction Q1 times Q2, where Q is the charges of the two things that we're calculating the force of attraction or repulsion between. And then we have the distance between those two objects squared. Our unit of charge, so this is a new unit for us probably, is the Coulomb, which we abbreviate capital C. Trying to think. We're going to do some practice with this formula, but I think for the purposes of this, I'm going to stop right there. So now put that page to the side, and I want you to try to find the next page I gave you in your bundle, which is 32.1. What I want to do actually is do like every other one of these kind of in this format, and then have you try to do the other half and take a picture and put it up on Google Classroom, and I will grade the half that I don't show you how to do. And that doesn't mean don't ask questions. Please email me if you get stuck on one, but hopefully if I do every other one, you can kind of figure out the ones in between. Okay, so we'll start with A. Label the proton in the nucleus with a plus sign and the orbital electron with a negative sign. So we know that the nucleus is in the middle, so I'm going to put my plus right here for my protons in the nucleus and a negative out here for my electron outside. So here is Coulomb's law. It says if the charge of either the nucleus or the orbital electron were greater, the force between the nucleus and the electron would be, and it's just a greater or less. Okay, so we're basically saying if either of these Q's was a bigger number, okay, it doesn't say positive or negative, but a larger, maybe absolute value, would the value of F increase or decrease? Okay, so our charges are on the top of the fraction. So if their product is bigger, that would make the whole right side of the equation bigger because they're in the numerator of the fraction, on the top of the fraction. So if the top of the fraction gets bigger, the whole everything gets bigger, so the force between the nucleus and the electron would be greater. Okay. If the distance between the nucleus and the electron were doubled. Okay, so a lot of these questions have, instead of plugging in real numbers up here, like telling us the actual charge and the actual distance, it's going to use, you know, this is doubled, this is half, this is a quartered. So I think the easiest way to do it is to pretend we're starting with every single number is a 1. Okay, so I'd have 1 equals 1 times 1 times 1 divided by 1 squared. And then just do to what you would do. So if the distance between the nucleus and the electron were doubled, so I'm going to plug in everything except for this number that was doubled as a 1. So I'm going to have the force is 1 equals K is 1 times both of my forces are 1, but the distance is doubled. So instead I'm going to plug in a 2 there, and you see in the formula that that is squared. And actually this one should be an X or a question mark. This is what we're solving for. Okay, so 1 times 1 times 1 is 1 divided by 2 squared is 4. So my multiplier of my force is a quarter. So my answer would be a quarter as much a force as there would have been before. Okay, we're going to kind of do that same thought process down here on the bottom half. Okay, so it says, consider the electric force between a pair of charged particles a certain distance apart. By Coulomb's law, if the charge of one of the particles is doubled. So again, I'm going to find what would happen to my force, and I'm going to plug in 1 for everything except what it says is changed. So I'm going to plug in a 1 for K, and one of the particles' charge is doubled, so I'm going to go 2. The other one is still 1, and it doesn't say anything about distance, so that stays. Okay, so 1 times 2 times 1 is 2, divided by 1 squared is 1, and that is just 2. So this is a 2, so my best answer is it would double. Okay, so again, if the charges get bigger, the force gets bigger. If the charges get smaller, the force would get smaller. Alright, so see, if instead the distance between the particles is halved, distance is halved. Okay, so again, so we're trying to find what would happen to the force. Everything we plug in as a 1 except the thing it says is changed. Okay, so K is still a 1. It doesn't say anything about our charges changing, so I'm going to go put both of them a 1. And it says the distance is halved, so I'm going to go 0.5 squared. Okay, so 1 times 1 times 1 is 1. Okay, and then 0.5 squared, you may be tempted to overthink that one. But 0.5 times 0.5 is 0.25. Okay, so then 1 divided by 0.25 is 4. So that means if the distance is halved, the force of attraction between them would be 4 times bigger or quadrupled. Okay, so go ahead and see what you think about that. If you need any help, let me know. Otherwise, finish the ones that we did not do and take a picture and put it on Classroom so I can give it a look-see. Later.